Hey, we're here at go2math.com. Click on the calculus. We're looking at numerical integration, and we're doing 2.1, I believe. So we'll click on that. And what's the chances of that coming up? Anyway, it says use Simpson's rule for approximating the definite integral with n equals 4. So like in the trapezoid rule, right, n represented the number of subintervals, and the number of subintervals here is going to be 4. It says out here round to 4 decimal places if needed. Now the thing about Simpson's rule is n must be even. Okay, n has to be even, and I wish I had time to get into the theoretical aspects of it, but what we're going to end up doing here is just stating the theorem of Simpson's rule. Alright, so the first thing I'm going to do, we'll go ahead and rewrite this 0 to 1 x squared dx. Alright, so you should know how to get the exact value of this. And by the way, let me go ahead and say this: f of x is equal to x squared, and we're on the interval between 0 and 1. Simpson's rule. Alright, so this is the way it goes, and like most theorems in calculus, we're going to consider f to be continuous. Right, and I believe f, and of course on an interval, on a closed interval a, b. So as you can see, our intervals between 0 and 1, right? So for approximating, we're approximating, this is a b, f of x dx. For approximating this, all right, we can actually say, and I guess I better write it again, x dx is approximately, all right, so I'm just going to state this, b minus a over 3n. So remember in the trapezoid rule it was b minus a over 2n, I believe, wasn't it? I'm trying to remember. b minus a over 2n, right. Okay, I had to cheat on that. Okay, so we take the first subinterval here. Of course, this has been actually factored out. F of x naught, and we'll talk about how to get that here in just a minute, plus 4 f of x1 plus 2 f of x2 plus dot dot dot, and then we'll come down here and say plus 4 f of x n minus 1 plus f of x n. Now you might be wondering, where are these coefficients coming from? 4, 2, and let me actually state this pattern. 1 being the first coefficient of f of x naught, and then 4, 2, 4, 2, 4. Separate this stuff by commas here. 1, 4, 2, 4, 2, 4. All right, dot, dot, dot. 4, 2, 4, 1, I believe. Yeah, it's because the last one, right, these last two must be a 4 and a 1 right here. Okay, so here's the coefficients, and this stuff is actually derived up, but we're not going to do that. All right, so you'll have to take my word for it. Okay, all right, so there's the theorem. As long as f is continuous on the closed interval AB, then we can approximate this guy, and that approximation is actually equal to this stuff here. Now, one thing I need to say here is that n is an even number. Okay, n must be an even number. All right, so let's go ahead and do this. So first thing we're going to need to know is delta x. So remember, delta x is b minus a over n, right? N being the number of subintervals. And so therefore we end up having 1 minus 0 over 4. Therefore delta x is 1/4. Delta x is 1/4. Okay? Alright. So I'll go ahead and state this. A plus delta x times I. The general. This is like the right endpoint once again. Okay? Just like in the trapezoid rule there. And so let's do x of 0. Alright, this is what we're starting with. We're starting, well, that 0 and that 0 is two different zeros, okay? This is just, never mind. X of 0 here, well, I mean, I guess not. Well, no. Anyway, okay, never mind. This is our A right here. That's what this guy is, right? From A to B. Alright. I know that kind of stuff always confused me. It still does, actually. Do certain problems. Alright, so first one, x of naught is going to end up being 0. And then let's look at x of 1. 0 plus 1/4 times 1 is equal to 1/4. X of 2. 0 plus 1/4 times 2 is a half. Whoa, is a half, not a fourth. Alright. And then we have x of 3. 0 plus 1/4 times 3 is equal to 3/4. And then last but not least, 0 plus 1/4 times 4, and that's what you should come up with is 1, because A is 0 and B is 1, right? Okay, now let's come over here, since we got some blank space here, and just and do this. All right, so the first one is that guy right there. F of x of naught is equal to, so we plug x of naught in, which happens to be 0, into our function. Now remember, and I should have stated this, what our function is. Remember, it's f of x equal to x squared. All right, so we plug 0 squared in and we get 0 out. All right, easy enough. Then we go to the next one, and that has a coefficient of 4, so I'm going to write that right there. X of 1 is equal to 4 times, now x of 1 is 1/4, so that becomes 1/4 squared, so that ends up being 1/4. Right, yeah. And so then our next one is 2f of x2. 2 times f of x2 is equal to 2 times, so we're plugging, come over here, x of 2 is a half, so we have a half squared, and then that just ends up being half. I'd actually think about that for a second. So we have 1, 4, 2. Okay, so this is gonna, let's see, x of 3. Yeah, alright, so we got another 4 then. Yeah, f of x of 3. So you see, this would be this guy right here. Alright, is equal to 4 times, so we take, look at x of 3, so that was 3/4. Plug that into the function. 3/4 squared, and let's see, 9/4. Is that right? 9/4, I believe. And so then the last one always has a coefficient of 1. This is the one we're looking at here. So this is just f of x of 4. And has a we'll just go ahead and write that 1 in there. So this looks like 1 right here, x of 4. So plug 1 into the function, and we end up getting 1 out. Alright, so we got all those guys. Check, check, check. Check, check, check. All right. Now, I'm going to go ahead and write this here. So we're going from 0 to 1, right? Here's our function, x squared dx. And it's going to be approximately, now remember this is b minus a, over 3n. Yeah, over 3n. So 3 times 4. Remember we had 4 subintervals. All right. Okay, so we've got that first one, so that's going to be 0 plus, and then 4 times f of x1, which is 1/4, plus 2 times f of x2, which is a half, and then plus 9/4 plus 1. All right. So this is going to end up turning out to be 1/3. Now, if you actually find the exact value of this, it turns out that it's 1/3, which is actually equal to this. So going out just 4 subintervals was sufficient. Now I should state that the more subintervals you go out, the closer to the approximation you're going to get to this. And of course, if n goes to infinity, right, this is n, in other words, this goes to infinity, then it's equal to our original, it's actually equal to the interval there. All right. So those are the steps of using Simpson's rule. Let's hit the answer here. Now, of course, I said round to 4 decimal places, even though you can't read it on the screen there. And 1/3 is 0.3333 repeating. But I just said let's just go ahead and round to 4 decimal places. So there you go. All right. So those are the steps on Simpson's rule. It's not too bad. You just got to remember that pattern on the coefficients and just, work the problem out several times. You can click here, click, 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 get some different ones come up, and see how that works out for you. All right, and compare that with the actual integral, the theoretical value. I guess you could say the exact value is. All right. So come on over to go to math, practice that. Maybe I'll see you there. Bye.